Hi guys, welcome back to Data Every Day. Today we are looking at a data set of various diseases. We actually have a bunch of symptoms. They're all binary variables, basically a yes or no for a given symptom. We have 132 symptoms, and then our prognosis at the end. So there's 41 unique values, and the nice thing about this data set is that each class is represented with the same number of examples. So we don't have to worry about class imbalance even across 41 different diseases. Now I'm going to use a method of feature selection. It's a bit of a simple method where we actually use the weights learned by a logistic regression model as a measure of feature importance. Let's hop into the notebook. I'm going to use NumPy and Pandas for working with the data. We're going to do some visualization using pyplot, Seaborn, and Plotly Express. And then for pre-processing, I'm actually not going to use the standard scaler, but I am using the train test split function from sklearn. And then we'll use a logistic regression model, like I mentioned, and we'll evaluate the results with the confusion matrix. So let's go ahead and import all of that and load in the data using pandas.readcsv. And I'm only going to use this training CSV file today. Paste that in and we can take a look. Alright, so we cannot see all of the columns, so I'd like to go up here and just include this option, pandas.set option, and I'm setting max columns to none. This way, when we reload the data, we can see all of the columns. Now, there are quite a few here. And I would like to point out at the end we do have a missing column that somehow got in there, even though it didn't show on the preview. So we're going to want to drop this. And we don't have to do any pre-processing on this data since everything is already encoded as binary variables, either 0 or 1. We also don't need to scale the data necessarily because they all take the same range of values. So it is min-max scaled in a sense because they're all binary. So let's start pre-processing. I'd also like to point out that if we take data and check how many missing values it has by summing over the is-and-a matrix twice, we should get, well actually we have 4,920, which corresponds to the total number of rows, and that's just because we have this column of missing values at the end. So I'm going to create a function called pre-process inputs. So we really don't have to pre-process much. All this is going to do is remove that column and then split the data frame into our 4 sets. So I'll start by creating a copy so we can maintain the original, and I'm going to drop this column to begin. So df equals df.drop, and the name of the column is unnamed 133. So I'll type that in like that, and we're dropping from axis 1. Now if I return df down here, let's say we store that back in x. I'm passing in data. Then x should just have 133 columns, so minus that 1 because we got rid of the 1 at the end. So we just have our prognosis and then all of the symptoms. And now if we sum over the is and a's of this, we get back 0 missing values in the whole data set. So last thing to do, like I said, is just split the data. So drop unnecessary column, or maybe I'll say missing column, and then we will split df into x and y, and we'll do this we'll take y will be what we're trying to predict, so it's just a vector of all of our class labels, and that's going to be at the end the prognosis column. So y is going to be df sub prognosis, and then x is all the rest of the data, so df.drop prognosis. And we're dropping from axis 1 again, which is the column axis, and we will do our train test split. So now we want to send 70% of the data to the train set and use the other 30% for evaluating the model. So I'll create 4 new sets of the data, xtrain, xtest, ytrain, and ytest. And we'll use the train test split function that I imported earlier from sklearn, which will automatically shuffle and split the data for us given a train size. We'll say 70%. And like I said, this will shuffle the data, and we want to include a random state, which is just a seed, so that we can reproduce the results from this notebook. Alright, and I believe that's it actually, nothing else. So instead of returning df, I'm going to return these 4 sets of the data. And we'll get them back over here and take a look at xtrain. So xtrain should just be 70% of the data, so not as many rows, without the prognosis column. The prognosis column is being stored in ytrain. And so these are all the labels, and I'd like to point out that if we look at the class distribution here, you can see we have a very similar class distribution for each category. And this is because if we look at the original prognosis column, we actually have the exact same number of each class. So when we do the train test split, we get roughly the same. Maybe I'll leave this up here so we can see it originally. Okay. So now we're going to do the training. And we're just going to use a logistic regression model. So let me say original data. And we'll create our model. This will be logistic regression. And we'll fit the model to the train set. Alright, once it's fit, we'll print out the accuracy value, test accuracy. And we'll display this to 2 decimal places and as a percentage since it's an accuracy value. And we can get the accuracy value from model.score. So the score function will return the accuracy in the case of a classification model. We just have to pass in the test set. And I want to multiply by 100 since we are looking at a percentage. And we actually come out with 100% accuracy. So this seems to be a pretty good data set. It definitely helps that we have even class distribution. But we also have a good number of features. We have 132 different symptoms. So it's very nice that we are able to get such a high accuracy. I don't know, maybe if we had a larger test set, we would have a lower accuracy, but it would still probably be very high. We do have 1,400 examples in the test set, so this is 1476 out of 1476 correct, which is very nice. And so now I'd like to do feature selection. So there are many methods of feature selection. We're going to cover probably the most basic one, which only works with linear models. You can do this with either linear regression or logistic regression. Basically, the way it works is when we fit the model, the way logistic regression works is we just have a single, at least for each class, we have a single vector of weights that are associated with a given with each column essentially. So we're going to take this value, multiply it by a weight. So everything in the itching column gets its own weight. Everything in the skin rash column gets its own weight. Each column has its own weight associated with it, and we can get that back with model.coef for coefficients. And these are the actual weights. If we look at the shape of this, we have one weight for each feature. There's 132 features. Each one gets its own weight. And then we also have one of those feature vector weight vectors for each class. So we have 41 possible diseases in ytrain or ytest. And so we end up with 132 weights for each class. Now, we can use these weights as a sort of measure of feature importance. Now, there are better ways, I would say, to gauge feature importance, but this is a very simple way of viewing it. Because if you think about what this means, let's look at them, right? If we have a really high value in a given location, let's see what the max is. All right, so we have the highest value in here is 2.3. Now, the feature that this is associated with, because it's so high compared to the others, this means that feature is very good at predicting positive. It's very useful for predicting positive class. Because it's so high, if we do have a 1 there, it's going to multiply by that 1 and contribute highly towards the positive classification. If we have a minimum, if we look at the minimum, that's negative 1.4, the feature that this is associated with is very useful for predicting negative class. Because when you do run it through the sigmoid activation, if it's a very negative number, it'll go close to 0. On the other hand, if it's a very high number, it'll go close to 1. So it ends up being, it's a way of thinking about the importance of each feature. So if we look at this coefficient matrix here, remember that the shape here is 132, one for each feature, and then we have one of those vectors for each class. So if I took the average across all classes, so now we take the average basically across all diseases, we'll get 132 values, where each one is the average feature importance across all classes. So if we take the numpy.mean of model coefficients along axis 0, which is this axis, so we will end up with just 132 values, where we just take the averages down the rows. And so this is going to be a single value of weights that have been averaged across all 41 classes. And this is a measure of how each feature, of how important each feature is, regardless of class. So you can sort of consider this as a method of gauging which features are more important than others. So what I'd like to do, I'd like to store this in coefficients. I'm going to call it coefficients. Sorry. And I'm going to, no, I guess I'll print it out here. What I'm going to do is create an importance threshold. So let's look at this. Alright, I'm going to create a new plotly figure, which will be a bar chart. And this is going to, we're going to give it a horizontal orientation. And on the x-axis, we're going to include these coefficients. On the y-axis, we're going to include the column names of the data. So xtrain.columns. If we print this out, we show the figure. We can see now the average feature importance across all classes for each feature. Now we can't, I believe we should zoom in to see all of them because there are quite a few here, so we can't see them all in the main view. But basically, yeah, so high values can sort of be thought of as useful for predicting positive, meaning they do have a disease for any class, right? This is averaged. And that really negative values could mean they're very useful for predicting negatively that they don't have a disease in a given category across all categories. Now, if we look at which this is, it says chills is useful for predicting negatively. This is a bit hard to interpret still. It's not so clear. Meanwhile, these diarrhea and dark urine on the are useful for predicting positively. So you can notice that there are some here, really small ones, patches in throat, for example, that are not so useful, at least according to these weights. So we're going to try to filter out the ones that are not so useful, these little ones, these ones with low feature importance. And we'll actually see this way if this is a good measure of filtering features, of feature selection. We can tell that by just training a new model on the reduced data and seeing how it does. So I'll just spruce up this graph a little more. I'll give it some color. I'm going to color it by the coefficients. I'm going to give it a color scale. We'll do red for negative, blue for positive. So I'm going to set the lowest value to red, and the highest value to blue. Then I'll just give it some labels, axis labels. So the dictionary x will become the coefficient, your coefficient value, and then y will be our feature. And we'll give it a title. Feature importance from model weights. Okay, and here it is. It's a little nicer to look at. The more red it is, the more negatively important it is, if that makes sense. The more positive it is, the greater, the more important it is for positive values, for positive classifications. Okay, so you'll notice that these are actually on really small scales. This is, I think, if we look at the maximum of this, coefficients, the maximum of coefficients, so after it's been averaged, before we were looking across the whole thing, you see we still have a really tiny value. And similarly, on the negative, we have a really tiny value, really close to 0. But we can still feature them relative to each other. Filter them. So how are we going to do this? Well, we can use the NumPy's quantile function to it will construct the distribution of this, and then we can select all the examples that lie under a certain quantile. Now I would like to point out we want to take the absolute value before we do this, because we don't just want to, like if we cut the threshold right here and said, okay, let's filter out all the ones that go before the threshold, then it would get rid of all of the negative features, which we don't want. We want to do it like this. We want to make it symmetric using absolute value, so that we filter out only the ones that are close to 0. So let's do this. I'm going to take a numpy.absolute value of the coefficients, and you'll see that they are now all positive. They've been all the negatives have just been reflected over the 0. So if we look at what that looks like here, numpy.absolute value, you can see they're now on the same positive scale. So now we can cut at the quantile threshold. Maybe we'll do if it's under 25 percentile or 0.25 quantile, we'll cut it out. We could try different thresholds though. So over here, we have this absolute value thing. I'm going to use the numpy.quantile function and specify the quantile that we're looking for. So let's say 0.25. And this will give us the quantile value, the actual value along this axis, where we find the 0.25 quantile. So any values that are below this value, it looks like it's lying maybe here. Anything below this value right here, on the left side of it, we will cut them out, and all these ones that go high, we'll keep. So what we'll say is, we'll actually call this importance threshold. And I want to graph the importance threshold here. I guess I'll put this here. All right. Or maybe over here. Alright, so we have our coefficients. Now I want to take off this absolute value down here. And now we're going to just add some lines to our graph with fig.add vertical line, v-line. And the x-coordinate that we want to add the line on is going to be the importance threshold that we just calculated. And the line color can be yellow. And we'll do the same thing, but for the negative importance threshold, because we want to show the effect that the absolute value had. Alright, so here it is. Why don't we actually also add a rectangle with a vertical rectangle dot add vrect. The first x-coordinate will be, it's x0, will be the importance threshold value, and the x1 will be the negative importance threshold value. Let's give that a line width of 0, a line color, is it line, fill color, we'll give it a fill color of yellow, and we'll set the opacity to 20%. Opacity 0.2. Alright, and so you can see the features. These are the features we're going to cut out. So anything within the yellow, we're getting rid of. Let me just mark that down. anything within, or any features whose weight values lie below, or say average weight values, lie within the yellow box will be removed. Okay. Alright, so how do we actually remove them? We can get the low importance features by taking the absolute value of our coefficients and checking if those values are below the importance threshold that we calculated. So if we look at just this thing, we'll actually get a true false, where the trues mean that those are the low features, the features with low importance that do lie below the threshold. False means it's past the threshold. So we can actually get the column names associated with those with xtrain.columns, and then using this as the indexer, using this true false vector as the indexer for the columns. And if we look at what those look like, these are actually the column names of basically the symptoms that were least useful for predicting, for making predictions, if you believe that this is a good measure of feature importance. Alright, so let's actually test this. Let's see if we can still maintain a high accuracy using the reduced data without the low importance features. So our reduced data is going to be our original data. Remember, we didn't modify this. This is the raw data, but without the low importance features. And we're dropping those from axis 1, and we'll make a copy, fresh copy. Then we'll recreate our xtrain, xtest, ytrain, and ytest using the preprocess inputs function that we created earlier. But this time we'll pass in reduced data instead of data. So now if we look at xtrain, you'll see we only have 99 features. So we had 133. Looks like we dropped about, we had 132 and we dropped 33 of them. So here are the 33 that we dropped, and these are the remaining. So let's see if we can still get a high level of accuracy. So I'm going to create a reduced data model that is also a logistic regression model. And we'll fit this model to the train set. This time, it's this new train set that we generated. And we'll print out the value with model.score. We're evaluating on the test set. And let me format this into a string like we had before. Test accuracy being formatted to 2 decimal places with a %sign, and we'll multiply this by 100 to give the percentage. Alright, and our accuracy dropped by about 0.75%. So really not that bad. It looks like maybe this is a decent way of performing feature selection. Maybe if we lower this threshold, so if we recreate this original model and take a look at the, we should take a look at this part where we specify the threshold here. Instead of doing 0.25, what if we just do 0.20, so the 20th percentile? Then this box gets smaller. So we'll filter out fewer features. So we have fewer in here. And if we look at this, we're back up to 105. So we kept 6 more features than we had before. And if we train this, maybe we'll get back up to 100. Not quite, but it's closer. So the more features we drop, the lower accuracy goes. Let's see if we make this really high. Let's say we make it up to 50%. We drop anything in the first half of the data, but anything below the median. I have to recreate our train data and then do this. Now we have a really big yellow box, and we're going to drop a bunch more. So you can see we're dropping a whole lot more features now. And we're down to 66 columns only. Now, this actually, we're still doing quite well. I mean, it's it's nothing like 100%. We're definitely losing important information that I wouldn't want to drop. But in this situation, if you're using a dataset with a huge number of features and many of which may be completely useless, this might be a good way to filter out features. But there's probably better ways, and I will cover more useful ways to filter features in the future. So let's bring this back down to, I'll do 25% again. Yeah, and we will, last thing I'd like to do is create a confusion matrix for this reduced data model. Alright, so first, to create the confusion matrix, we should generate some predictions. So ypred will just be the vector of predictions for each training test example. So we'll use reduced data model dot predict on the test set, and if we run this, you'll see it will return the actual disease names that it predicts for each X-test example. Then we can create a confusion matrix. I'm going to store it in CM using the confusion matrix function from sklearn. And we'll pass in the true values and the predicted values, and it will make the comparisons and generate the matrix. And then we'll plot the matrix using pyplot and Seaborn. So I'll give this a figure size of 30 by 30 since we do have a lot of classes. And we'll generate a heat map from Seaborn, passing in the confusion matrix, turning on annotations, formatting it with a G like this to show up the actual classification counts as integers instead of in scientific notation. Then the minimum value we'll set to 0. We'll give it a color map of blues, and we'll turn off the color bar, so we don't really need it here. Then we'll give it some axis labels. On the X we have the predicted values, on the Y we have the actual values, and we'll give it a title, which will be confusion matrix. And the last thing I want to do is set the tick marks. So we'll have the X ticks. I want to show the actual column names, the feature names or disease names along each axis. So first we want to specify the spacing. I'm going to use a NumPy A range to generate 41, one for each class, unique spacings. So it will go from 0 up to 40, and that will actually correspond to the corner of the heat map. So I want to shift it over to be in the middle of the box by adding 0.5 to each value in the A range. And then as the actual label values, we're going to use the classes from reduced data model. So we can get that with .classes underscore. And I want to be sure to rotate the x-axis ticks by 90 degrees so that we have them pointing that way. And similarly for the y-axis, this will just be y ticks. We want to rotate it by 0 degrees so that we keep it horizontal. Alright, and let's see how this is with plt.show. And this might just take a moment to load up since we do have quite a few classes as to generate a big matrix, a big heat map. Here it is. So it is quite big. Let me get it in a new tab here. And you can see we're doing really well in each class. We only have a very few misclassifications. Overall, it's really good. I think we ended up, this was with a 99.25% accuracy. So we have very few misclassifications. Overall, the model is performing extremely well. Yeah, and so that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.